Hi guys. Um, Today, this is the second video of June 19th of the workshop series, and also probably the final one that I'm going to do before I let you guys loose for the rest of the project. Today we'll be talking about CAD concepts. So CAD stands for Computer Aided Design, and when someone says they're CADing or 3D modeling, all they're doing is they are making something in a computer software, maybe like a 3D model, so that they can produce it in real life. So like you can use 3D printing, you can use CNC machining if it's 2D, or like some sculpting methods or some resin methods to turn what you think of the 3D object from a virtual perspective into real life. So what we're doing in this workshop is we are going to be creating a case or something to mount our PCB that we designed in the previous workshop. So in the Altium Designer workshop, we went ahead and designed a voltage regulator, which takes in a unspecified amount of voltage and regulates it down to 5 volts and 3.3 volts. Now, this is really useful because usually we can take the 5-volt line and put it into an Arduino, which will power all the circuitry inside of that. Or we can take the 3.3-volt line and put it into some sort of wireless communication protocols. And so the purpose of this workshop is to teach you CAD concepts, but also to teach you that we can merge some electrical engineering concepts with CAD concepts to support your project ideas for it. So as always, for those in Zoom, if you have any questions on how to do any of these concepts, or you want me to backtrack, or you want me to do anything, just feel free to just speak up at any time and tell me to stop and back up. For those of you who are watching later, if you guys are confused about anything, feel free to ask me some questions in Discord or just talk in the server, and I'll be looking out for that. So I want you guys to learn this. And what I'm designing here is just a basic like trophy mount for the PCB, but in the future, if you guys are looking to put the PCB, the power PCB on some component of our design, you can always design a new mount for it. And so I'll go ahead and share the current PCB or the current state of what's going on. Okay, so this is the PCB that we've designed for, sorry, hold on, my music stopped. This is the PCB that we intermittently designed for the voltage regulator. As you can see, we have our V in here, and then we have an output for 5 volts and 3.3 volts. Okay, let me get just pull up my music back again. I need to have music play in the background, or else my headphones turn off. It's kind of some like power safety feature. So if no one's talking for a really long time, it just blanks out. Okay, give me a second. Okay, that should be fine. All right, so in the previous PCB workshop, we designed this little PCB here with mounting holes. And the purpose of these mounting holes, like I said, was to put screws inside. So my personally favorite screw is the M2.5 by 6 millimeter screw, or the M2.5 screw by default. 2.5 stands for 2.5 millimeters in diameter. So this 100 mil hole will approximately fit the 2.5 screw perfectly. And so since this hole is like in the center of it, we can like screw it into something and the PCB will just like hang from there. So in order to mount something to a 3D object, this is pretty important. So starting from this point, I'm going to go ahead and first teach you how to extract the STL file from this PCB. Now, remember from the PCB, if we press the 3 button, we can actually see the 3D model of what this looks like. We have terminal blocks here. We have some SMD chips. We have some capacitors. We have some AMS 117s. It's all pretty cool. But did you know that we can actually turn this into an STL? So all you need to do is we need to go to export, and we need to export it as a step 3D file. Now I'm going to go ahead and put this inside my Banshee demo project in Altium. And I'm going to go ahead and just export all. Okay, so this is done. Now, I'm going to get back to that in a second, but before that, let me show you exactly what I'm talking about when I say PCB mount. So this is the PCB mount for my Blinky Learner soldering kits, in which I have made for the soldering workshop. We can see here that this bottom piece is basically what we're going to look for. This bottom piece allows us to put a battery inside and screw it shut using a cover, and also has a neat little design in the back with the Hyperloop logo on it, and the top perfectly fits our PCB here. And I'll teach you how to do some projection tricks in order to do that. So this is what we're looking for. This PCB mounts directly into the center of the top mold, and it allows us to screw it in. Even the 3D printer even prints these screws out. So it allows a really tight fit, a really nice tight fit. Okay, so in that case, I'm going to go ahead and create a new file. And I'm going to put this file inside the UAV Banshee Robotics. And the summer, I'm going to put inside case demo. Okay, new design. So in Fusion 360, you want to first go ahead and go to the File button, and you want to click New Design, right? And this will give you a new 3D plane in which you can start building it. But before we do that, I have to import something. I have to upload something. And I have to upload my step file that I imported from Altium. Now, a step file is basically a 3D modeling file, and it contains instructions. It contains instructions for the 3D software on how to reconstruct that diagram. So if I go to documents here, I go to projects, and I go to Banshee demo, I go to vreg step. I'm going to drag this inside Fusion, and it's going to start uploading this into the software. So the step file gives it instructions on how to rebuild this file inside of the 3D window. And so just give it a little bit of time. Calipers go. Okay. It's taking its sweet time. Can't do anything else while it's loading, so just give it a moment. Actually, I can do something while in the process. Okay, let's talk about tolerances while it's taking its time uploading. So tolerances are really important. And if you look here, we are going to be putting a 9-volt battery inside of our 3D design. Now, this is really important because when you print things out, let's say if you 3D print stuff, you have to understand the chemistry of the material you're printing it in. Usually, we print things using PLA or polylactic acid. This is a type of plastic, something like this macro board is made out of, this kind of material. When you print it out, it is heated to approximately 200 degrees Celsius. And so when it cools, it actually shrinks. So when you're catting something for, let's say, a 9-volt battery, and you use something like a calipers, right? Your calipers to measure the distance between one end of a battery and another. Let's say this is exactly 1 inch. If you put exactly 1 inch into your 3D model and you print that, it's going to be too tight. You're going to be like, I can't fit this battery through the hole because my 3D model shrunk. It may have injected the plastic onto the bed at 1 inch of a distance, but when it hardened, it shrunk down to 0.9 inches, and suddenly your battery is no longer fitting. So that's what tolerances are for. When you are measuring anything, let's say when you're measuring this, you always want to give it a little bit of tolerance. So you always want to push it a little bit backwards, just so you can wiggle the battery around inside. And this tolerance is 0.1 of an inch. So 1.1 inches, I can freely put the battery in and wiggle it around. And so I'm going to use 1.1 inches to CAD the size of the battery instead of 1 inch, because I want the battery to freely fit into my 3D design even after it shrinks. So we are compensating for that shrinkage by giving more tolerance on the battery. I like to use millimeters to CAD because I think it's just easier overall. So I'm going to go ahead and give you some test measurements. So for this battery, let's say this is the length, this is the height, or sorry, this is the length, this is the height, and then this is the depth, right? This area right here. So in that case, if I go ahead and measure the length directly, and if I clamp it as hard as I can, it says 25.76 millimeters. Now, if I put 25.76 millimeters in the 3D design software, it's going to be impossible to fit this battery because that's too small of a tolerance, right? So I'm going to go ahead and extend these jaws a little bit, and I'm actually going to use 27 millimeters. And using 27 millimeters, I can freely put the battery in, and it can wiggle around, right? And it's not going to get stuck in my 3D model.
So you said during the 3D printing process, it would shrink down?
Yes.
By how much?
I don't know.
Percentage?
I don't know. It's usually a 5% tolerance, though. Again, it's due to the chemistry of the plastic you're working with. So if you are printing using PLA versus if you're printing using ABS versus if you're printing using TPU, it shrinks differently. And also shrinks depending on your printer. There's a lot of variables in place in which it changes your output. So in general, just give it like a large tolerance. For my printer specifically, I like to give it a 1 millimeter to 1.5 millimeter tolerance. That's usually what I call a tight tolerance. So that means I can fit the battery in, but it'll still be like secure. It'll be snug, right? It won't have the ability to wiggle around too much, right? But if you get a larger tolerance, of course, it'll wiggle around. So you just have to know your printer's parameters and how you're manufacturing it. Of course, if you're doing something like CNCing it onto like a board or something, CNC is more exact, right? Your wood or whatever you're drilling this into won't shrink after you drill into it. So therefore, you won't have to have that much of a tolerance. But for 3D printing specifically, since it's like this 3D modeling, hot plastic, hardening, chemistry just gets out of whack, you have to like make sure you know this well. And this takes experience. And if you're going to be modeling for this project, I'll let you know if the tolerance is not enough, because I have experience with my printer and I know that, like by experience. But in general, just make sure you don't like put the measurement that it says on here when you're like holding it really tight.
Yeah. So for what material will we be using for this project?
We will be using PLA and TPU.
Got it.
Yeah. So PLA, polylactic acid, usually melts around 180 degrees Celsius, but we print it at 200 degrees Celsius. TPU is the rubber material. Tolerance doesn't really matter for TPU. I'm going to regret saying that in a little bit, but TPU is rubber, so it's elastic. So that means you can like bend it and it's flexible. Not so much for PLA though. In addition, if you want some really strong parts, you can ask me to print in resin, but resin is a little bit scary. Resin is kind of like this chemical that hardens under UV light. So there's this like little, it prints upside down basically. You have a vat of resin down here, and you have this arm that goes down and touches it every once in a while. And on the bottom, there's an LCD screen that flashes an image layer by layer. And as it brings itself back up, it basically prints it upside down. And resin is really hard. So if you want some really secure joints, really hard joints, you would want to print in resin. Another thing I want to talk about. So I already have the dimensions of this battery, but just, you need to know that you don't always, you don't measure the exact dimensions of this battery. You always give it some 5% tolerance. And if you work with like 3D printed things a lot, you'll know the tolerance like from the back of your hand. So I know my printer has like a 1 millimeter tolerance to 2.5 millimeter tolerance for these kind of things. The dimensions of this battery is 26.5 millimeters by 19 millimeters by 57.15 millimeters. What else do I want to say? Oh, okay. When you're 3D printing or when you're designing anything for 3D printing, to just get this to your mind like really quick. 3D printers print from the ground up, usually. I have a printer that prints at a 45-degree angle, but most printers print from the ground up. And let me go ahead and just disable my screen so you can see actually what's going on in the background. Okay, so most of the printers you see back there, like let's say that one, that prints from the ground up. So if you want to print something called an overhang, in which it's like printing a structure that has no support to the ground, it's going to fall, right? Because you need to have support in order to print from the ground up. You can't just print something like in the air. That doesn't work, right? Theoretically. This printer right here prints at a 45-degree angle. And if you want to print a complex shape or a really long shape, this printer is the best for it. It's a CR30. And you may be able to neglect some supports. That means you have to like put some supports on. It can print shapes without support at 45-degree angles. So whenever you're CADing something, you always have to keep in mind how it's going to actually print it out, right? Let's say you want to print an arc like this shape. Is the top piece going to be supported if the nozzle prints from the ground and starts going up like this, right? And usually the answer is yes. Arcs can print pretty well. You just can't have like a overhang bridge because the plastic's going to fall down and you're going to be unhappy with the print because it's going to be a fail. Okay, so I went over tolerances. I went over supports, and I'll show you more about supports when we go into Kira. But those two are the main things you need to care about when you're doing CAD, even before we even touched CAD, right? How is my print going to actually print? How is my thing going to print? Okay, going to CAD now. Okay, so if we go ahead and take a look at the VREG model, we can see that this is what our PCB looks like. Now, this is what it looks like without any of the traces. It doesn't actually put the traces on, unfortunately. But in general, it's pretty good. It gives us the outline, or just like a bare outline of what the size of our PCB is. And so this will allow us to design something for it without actually knowing what the size of the PCB is, which is great because that's what projection is. So we have our PCB in which we're going to design around it, right? And I'm going to go ahead and put this into my main body. So this is the case. Okay, so to begin any CAD model or anything regarding CAD, the first step is always to begin your initial sketch, right? So the initial sketch is a 2D shape in which it goes on either the X, Y, or Z axis. Eventually, in order to make this 3D, you do something called an extrusion, right? You're going to extrude from this 2D shape into a 3D shape, okay? But everything starts from a 2D sketch, right? So a 2D shape like a square or a triangle or a more complex shape like that. All right. So I'm going to go ahead and quickly import this VREG PCB into my current design right here. And I'm going to move it upwards. I'm going to move it up about like 1 inch or so. And I'm going to change the document settings so I can CAD in millimeters, because that's usually better for me. Okay, so inside this CAD model, let's go ahead and first analyze like the components that we see here. How do we measure the dimensions of this PCB? We use the inspect tool. If we click the inspect tool and we click one side of the PCB and the other side of the PCB, we can see that this thing is like 85 millimeters long, right? And we can also see that it is 25.4 millimeters wide. At this point, I'm thinking in my head, how do I want to put the battery inside this PCB model? How do I want to structure everything so that this will be a great case that I can mount this PCB on and have this be kind of like a 5-volt supply and a 3.3-volt supply, right? So I go back to my measurements. I see that my battery is going to be these dimensions right here. 57.15 can be like longwise. 26.5 cannot be this wide because it's going to like extrude out from this area. And 19 millimeters can. So I'm going to put the battery on its side underneath it. And this brings up a good point that I can't directly show you right now, is that whenever you're CADing, you always have to have a picture in mind of what your CADing is going to look like and how it's going to function, right? So what I want to do is I want to build a case for it, right? So I'm going to go ahead and use the outline of this board as my initial sketch. Okay, so whenever we're doing anything CAD related, the first step to do is always to start with a sketch, always to start with a 2D image, okay? So I'm gonna go ahead and create a sketch, and I'm gonna create it on the X-axis right here. I clicked on the X-axis, right? If we see the cube up here, X-axis is like over there, Y-axis is like over there, and then Z-axis is like from bottom to top. So what I'm going to do is I'm currently CADing on the XY axis right here. Okay. And I want to use the outline of this PCB in order to start creating my own thing. So what I'm going to do is I'm going to go ahead and press the P button. P is something called project geometry. It's very powerful. And as electrical engineers, we don't really normally CAD from scratch. If you want to CAD from reference, you want to use project geometry a lot. What this does is it allows you to basically take whatever the outline of this shape is and bring it all the way down here, right? So I projected the geometry from this PCB down to my shape here. And this basically gives me the freedom to do whatever I want now. because what I have here is a rectangle, a curved rectangle of whatever I drew in Altium, but now it is in Fusion 360. So that is project geometry. Now, in case you want to like, draw your own thing, right? In which I know that's probably what you're going to ask me. You can use the Create tab to make rectangles, circles, whatever you want. So you can make rectangles right here, and you can manually edit the size of these rectangles to what you prefer, right? But I'm not going to do that here because I already have my rounded rectangle. So everything in CAD starts from a 2D plane, a 2D sketch, a 2D shape. If I press home and I see an isometric view of my current design, it literally just looks like a rectangle, right? And this is basically going to be my base for the mount. This is really important, all right? So if I press finish sketch, I'm left with this rectangular shape here. In order to turn this from a 2D model to a 3D model, my next step is to use this function called extrude. Extrude will take my 2D model. I'm going to select everything in my 2D model, excuse me. And I am going to then bring this upwards, or I'm going to bring this downwards actually, and I'm going to tell you why later. I am going to bring this downwards, and I am going to say that, okay, I want to fit a battery inside of this, and I remember that my height is around 26 millimeters. I'm going to bring this down to 30 millimeters here. Okay. Okay. So I brought this down all the way to 30 millimeters, and I'm going to press OK. And now suddenly we have a 3D shape. This is going to be known as a body or an object, right? And this 3D shape came from the fact that I made a projection of the PCB onto a 2D sketch in the XY plane. And then I finished the sketch and I extruded it 30 millimeters downwards to become this shape right here. Looks like a...
extrude?
The extrusion button is in the create menu, and it's just this icon right here. So you press this extrude button. When you press it, you have to select the sketch. So if you don't have a sketch first, you'll be able to select this option. Okay, so if I go ahead and show this regulator board again, I can see that at the top here, this directly matches up with my bottom figure. So I can drag this cube around the top right corner to look around this diagram. So if I want to mount this PCB to the ice cream sandwich cube that I just created, I need to drill some holes, right? And so I'm going to go ahead and start with holes because I think that's a good segue into the batteries and everything like that. Okay, so let's say I want to drill some holes into my PCB. I mean, my 3D model, right? Here's the thing about holes. Holes are great, but also you got to mind your tolerances. Again, if you're making a through hole, there's two types of holes mainly, right? There's one type is which you got to screw into, and the second one is where you got to put it all the way through. So like a very loose hole. Something like if I wanted to put a eraser through this hole right here in the design, I can put it right through, and it's gonna go like, it's a very big tolerance, right? That means I can put it through and it's gonna fall down. A very tight tolerance would be, for example, like this screw right here on my macro board, right? I can't pull this screw out. It's meant to hold the top piece and the bottom piece together. So in fact, if I actually unscrew this, you'll see that the top piece right here, this macro board is broken down into two pieces. This top piece right here has a loose tolerance. The bottom piece has a tight tolerance. And that way I can go ahead and screw the top screw into the bottom piece while clamping the middle part down. Does that make sense? So what I'm saying is that the piece right here, the top cover has a loose tolerance, right? I can put the screw all the way through and I can like wiggle it around. But the bottom piece has a really tight tolerance so that when I screw the screw into the bottom piece, I clamp both pieces down. And that's what we have here, basically. Our Altium design has holes that have really loose tolerances. I can put a 2.5 by 6 millimeter screw through this really loosely. However, I want to make the holes on my actual 3D model really tight because I want to screw the PCB on, right? So in order to make the holes really tight, all I got to do is I got to select the hole option, and then I got to select these four corners. Again, because I've already projected the geometry onto this figure, it's really easy for me to like use this as a reference to connect with the PCB that I designed. Okay, now we have this menu here. Whenever we're making a hole in Fusion 360, it always brings up kind of like a hole wizard for us. And in this hole wizard, we need to determine what kind of hole we're building. In this case, since I want a really tight tolerance hole, I'm going to make this a threaded hole, right? I'm going to make this a threaded hole so I can screw a screw inside of it. So in this case, I'm going to go ahead and select the tapped option, which will give me the indications like the twirly bits inside the 3D model. I'm also going to make this a flat and that's pretty much it. So again, you got to know what kind of screw you're drilling into this. You need to get good knowledge of screws, in which I can link a video to you guys later. I actually held a workshop with Hyperloop on identifying screws and how to use screws in designs that I think would be really useful. But in this case, I'm going to use a M2.5 by 6 millimeter screw. So I already know what screw I'm going to use, right? So in this case, I'm going to choose the anti-metric M profile screws, and I'm going to choose the 2.5 millimeters. In general, there's only two types of screws you'll ever use, the imperial screws or your metric screws. In this case, metric screws will be better because I've already like designed the PCB for it. So in this case, I'm going to choose M0.35 because it gives it actually a bigger tolerance. If you see this number down here, this is the hole width. So 2.0676 millimeters compared to 2.171 millimeters. This is actually a huge difference because remember, this is going to be printed in PLA. So when PLA shrinks, it's going to be really hard to drill a hole through, which is why making it a little bit wider will make it a lot better in the long run. So the hole depth, I'm going to make it 5 millimeters because I know this is an M2.6 millimeter screw, which means it has a 6 millimeter depth. But the PCB is already going to take some of that. So I'm going to make it a 5 millimeter depth instead. I'm going to model this so that it actually prints this out. And I'm going to press OK. Now I can check this. My PCB has a thickness of how much? It has a thickness of 0.411 millimeters. So in fact, 5 millimeters is being a bit generous. I think it should be actually about 6 millimeters. I'm going to go change that real quick. So what I'm thinking right now is if I'm going to drill a screw into this design, will it tap out? Will it hit the bottom before I've actually drilled the entire thing in, right? In this case, if it's an M2.5 by 6 millimeter screw, then it needs to have a 6 millimeter depth. Okay. All right. Now we've drilled the holes in, which means that we can mount the PCB directly into this top block here, right? If I go ahead and move this piece, if I move it downwards into this design, you can see that the holes directly match up with the PCB here, right? And I can go ahead and put a screw straight into this design. What would be the problem if there's extra space before the screw bottoms out? Your screw is going to stick out of the PCB. That's the problem. It looks ugly. You can kind of force it into it, but in general, like if your screws are flat.
I meant the other way. What if there's like, what if you made it 7 millimeters depth?
Oh, that's fine. It doesn't really make a difference. It does make a difference if you have something below it, right? Let's say you have a battery below it and the screw goes straight into the battery cage because I'm going to have a battery cage right below it, right? So I haven't designed the place I'm going to put the battery yet, in which it's going to be somewhere down here. But in general, what I just described to you was just how to correctly tolerance your screws. In that if it's a 6 millimeter screw, generally you want 6 millimeters, right? It's not going to go over. So knowing what you have, knowing what you're going to use to build your design is really important beforehand. So let's say for the PCB, I need to know my bill of materials. That's kind of like the same analogy.
And the bottom of the PCB, is it flat or there's pins sticking out?
Good question. There will be pins sticking out. So that was my next point. To compensate for the terminal blocks being there. So if you notice that the terminal blocks are actually they actually have stuff sticking out on the bottom of them, you can actually kind of cut them off. You can either cut them off or you can just leave them there and compensate for it in the 3D model. So in the 3D model itself, I'm actually going to create a little bit of a divot in the bottom to allow for this little tip to occur. So I'm going to go ahead and measure this. And this little area is actually about 3 millimeters. So I need to make a 3 millimeter divot on the bottom of this PCB design to compensate for the terminal blocks being there. So in this case, I will go ahead and create a new sketch. Invert position. Okay, so I'm going to hide this sketch for now, just so I have like some peace of mind. Okay, so I know in general that the terminal blocks are around here, here, and here. Now my dilemma is, okay, as a 3D modeler, I want to optimize a couple of things. One of the main things I want to optimize is how fast it takes to make this design. How fast does it take to print this design, right? If I have this design printed faster, that would be way better for me, right? And how can I make this print faster? By having less material. So I'm going to go ahead and I'm actually going to start cutting out some material from this top face. And I can go ahead and do that by first using the 4 corners as a reference. Now, there are many ways to do this, right? I'm just showing you my way of doing it. So I'm going to go ahead and use these projection points, actually. So I need to project it from that sketch to this sketch. I'm going to go ahead and project this again. And now I have my own projection of this sketch here, and I can use these points as a reference. So I can then create a rectangle based on this. And I can see exactly where these little terminal block things will stick out, right? I'm going to go ahead and just cut it all the way down because I don't really feel like printing all this middle area. I can save space if I just like make this a round border and have this middle piece go all the way down. So in that case, what I'm going to do is I'm going to create an offset, and I'm going to create an offset by making some circles here. And this part is purely just a
Wait, how did you do that from where you cut out the middle, like in the?
So I drew a rectangle connecting these 4 holes together. And that created a little section in the middle of this PCB design.
Got it.
And then I'm going to create these circles so that I can avoid the holes. I can create some offset for the holes themselves, because when I'm drilling them in, they kind of need some support as well.
Mhm.
So then that creates this little middle figure, which I can highlight. And I'm actually going to finish the sketch, and I'm going to extrude this part down. So including these little terminal block holes. And Ollie, exactly what you said, I'm compensating for the little pins on the terminal block. Oh, frick. The pains of catting. All right. Usually you want it to show the top. There you go. Okay, so now I measured the terminal block holes as 3 millimeters, but in order to give this a little bit more room, I'm actually going to put it as 4 millimeters. Just as a tolerance. Now, when I do this, I have to keep in mind a few things. Like, is there anything below this I need to like care about? Like, is there anything below this little figure that's going to interfere with my extrusion? And because there's not, this is fine to do, right? I just have to remember, if I'm making the battery carriage below this, like I have to think, okay, I can't make it 4 millimeters below the top, or else it's going to ram into this figure and I'm going to have issues, right? So basically what I've just done here is I've given the voltage regulator PCB room to fit into the into my 3D model itself, right? If I go ahead and move this all the way down, right? If I move this all the way down, and I go ahead and you can press Control 5, I think, to have an X-ray view of what's going on inside. This pin will actually not touch the bottom, and the screw will also be supported by the around area, which is good because now we basically can section off this top area as complete. We have a way to mount the PCB onto the 3D model that we just catted up. We also have some room to screw it in, right? And we can avoid the terminal blocks hitting the bottom, the terminal block pins, I mean. Because although you can cut it off, it's generally, that's not advised. For terminal blocks, at least. For resistors, you can. because terminal block pins are thick. So if you just check all the way around the X-ray view, you can see that everything is nicely accounted for, and there's no conflicts. There's no spacing conflicts. Okay, I'm gonna go back to the previous view. Now that our PCB is complete, we have to focus on our battery, right? Because our battery is going to be stored somewhere in the middle of all this stuff. And I'm going to think that I'm going to put the battery like smack dab in the middle in this front face here. So what I'm going to do is I'm going to make sure there's enough room for the battery. In that I'm going to go ahead and just inspect this element from the top to the bottom. It says 30, right? And I know it's 30 because I made it 30. And if we're going to be placing our battery like in this orientation into the middle of this diagram, we have to be careful of, let's say, this long side is going to be 26.5 millimeters, right? And we have to remember that we have a screw hole going down 6 millimeters into the top of this design. So in order for it not to be an effect, we have to kind of just like internally diagram our module out. So if we have 6 millimeters from the top, right, that's going to be our screw. So it's like if we're looking at this from the side, we have 6 millimeters at the top for the screw, and then I want to make a wall of 2.5 millimeters, right, separating that from the battery. The battery is going to be 26.5 millimeters. And then we're going to have a floor of 2.5 millimeters. So from top to bottom, this is going to be our like floor plan, right? And then in total, this is going to be, can't quick maths. 6 plus 5, 11, 37.5.
Yeah, 37.5.
Right? 37.5 millimeters. So in this case, this is too small. Now this is a good technique to do whenever you're CADing anything, just like to floor plan your way through like what you're going to be making it wide, to just so that you don't have to guess. This is very practical CAD, right? Because you're going to be making this in real life. I know one of my friends is in a CAD class right now, and she's a graphic designer, and so they had to make sculptures. And so what she has to do is make some like household objects just using CAD, and she doesn't like care about the dimensions of it. It just has to look nice, and that just like I guess triggered me, because I was like, if it doesn't have the correct dimensions, how are you going to make it in real life, right? Everything has to be like proportional to each other in that sense. So I guess practical CADing is really important here, just so that you understand like where things are going in your design. Okay, I'm going to go ahead and reference this extrusion. I go ahead and click the little rectangle in the bottom timeline here, because I need to modify this. This is going to be negative 37.5. Okay, now I'm going to go ahead and make a sketch in the front area. And in the front area, what I'm going to do is I'm literally going to map this diagram out, right? So I'm going to have 6 millimeters for the screw, in which I'm going to go ahead and make a line stretching all the way across, and I'm going to dimension this, and I dimension it using select dimension. That's how I space things apart from the bottom to the top. So I'm going to say 6 millimeters. This is going to be my screw, right? I know that if I press Control 5, there's going to be a screw right here, and it's going to go all the way down to 6 millimeters. So what this does is just, it gives me a area to see what happens, just like to tell me that I can't go there. I can't design there. I can't design a battery cage there. Okay, my second line, I'm going to have it as my wall, right? So I'm going to make another line. And these lines do not have to be like correctly dimensioned or anything. This is just like as a reference for me to like understand. So 2.5 millimeters, that's going to be my wall. And then down here is going to be my battery. My battery is going to be 26.5 millimeters. 26.5. Oops. 26.5. That. And then what I should have at the bottom here is the distance between the last line and the bottom should be 2.5 millimeters, right? And then I have verified that, okay, what I had in my head is right. When my math is right. And you'll find out that soon, CADing actually has a lot of math to it. A lot of basic addition, subtraction, and multiplication, divide by 2. because now we have to find a way to center the battery in the middle of this. We have to create a hole. We have to basically carve out a hole in the middle of this design to place this battery, right? So what we do next is we say, okay, I'm going to go ahead and find the center of this shape right here, of this rectangle. I'm going to go ahead and say inspect, and I'm going to draw 2 lines there, and it's going to tell me that's 77.47. So 77.47 divided by 2 is going to be 38.74. So I'm going to go ahead and draw a line in the middle here. Usually usually Fusion 360 will already tell you what the center is, but in this case, I just want to verify. So I'm verifying that the center is the distance between this line and this line is going to be 38.324, which is not correct. So I'm going to go ahead and actually move this. Oh, you see this? This tells me that it's not a straight line. So because it's not a straight line, I can't have this in the middle here. Okay, usually in this case, if you see the triangle there, that means it's a midpoint. That means Fusion 360 has already found the midpoint for you. In this case, I can just draw all the way to the bottom and verify that it is the midpoint of this rectangle here. So 38.735 is my correct answer. Great. So what I'm saying that is that the battery cage has to go somewhere in these 2 areas here. It has to be centered around this area, right? So 26.5 is the perfect wall height for it. But then I need to make sure that the horizontal area is 57.15 millimeters. Okay. So now I need to make a
Question: why don't you, instead of using the 26.5 side going up, why don't you use the 19 millimeter side? So it would be laying down.
right. I think I talked about this before, but if I make the 19.5 millimeter side on this end, then 26.5 will have to be like across, right? But if we go ahead and inspect this area here, we find out that this length is 25.4, which is shorter than 26.5.
Got it.
So if you want to do that, you can, but you got to remember to like extend the size a little bit. It's just a design choice. So depending on what you want to do, you can do that. That's what I'm saying. But in the context of what I'm doing here, it's better if I just make it like this in the center. Okay, so I'm going to create 2 more lines. And remember that I'm going to make the side battery wall around 57.15. So half of 57.15 is 28.575. So I need to make a straight line here and dimension this to be 28.575. Okay, so the end of the battery carriage is going to be over there. Now I'm going to do a quick little trick called a mirror, so I don't have to create another line on the other side of this. And to mirror, I just select the object, the line in which I want to mirror across, and just click OK, and it creates a new line that's directly mirrored from the left. So just like a mirror flipped. And now the mirror tool is very useful for this. Okay, so now I understand that these 2 compartments will store my battery for me. And that's basically what I want to get out of this. So I'm going to finish my sketch, and then I'm going to extrude this column, and the inside is going to be 19 millimeters. So I'm going to extrude this all the way inside. I'm actually going to put this as 20 millimeters because I want some way to cover this area when I'm not using it or when I'm successfully installed the battery. So I'm thinking about, if I have this in my hand right now and I'm using it, like, how am I going to use it? Am I going to have the battery carriage like uncovered? Am I going to have it like just falling out a little bit? Probably not. So that's why I'm doing this. So I'm going to make it actually 21 deep, just to give it some tolerance. Now, in general, for my 3D printer, your walls, if they're 2.5 millimeter, they're generally okay. 2.5 millimeter is kind of like the standard, I guess, I use for walls. This distance is 4.4 millimeters, which is fine. Okay. Actually, in this case, I would actually want to make the floor 5 instead of 2.5. So I'm going to add another 2.5 to my sketch here. 5 millimeters gives it a little bit more safety, I guess. like a little bit more safe room for me to design with. So in this case, this would actually become 40 millimeters. And I would have to edit my sketch in the back to be 40 millimeters. Okay, yeah, see, this is a little bit thicker, which gives me a lot more confidence when actually making some covers for this. All right, so this depth is actually going to be 21 millimeters, in which that's good enough for the battery. So it's going to be able to slot fully in, and it's going to have 2 millimeters of a blank space in which I can put like a cover on or something. So that's great. Let me go ahead and start designing for that cover. But before I do that, let me go ahead and check with the PCB designs to know which side I'm going to put this on. So in this case, the V in is going to be on this side. So if I put the battery into this slot, I can actually go ahead and route the wires through the side of this, let's say the side of this PCB here. Because again, it's 6 millimeters deep, so the wires are going to fit anyways. And I'm going to say that if I put this in here, if I put the battery inside the actual design, the wires can be routed through the 3D model.
And I'm going to try to from the top, bottom up.
I think I'm actually going to put it on the top. So I'm going to drill a hole straight through this area so that I can put the wires through when I 3D print this.
Got it.
And so this is just an example of something that you can do electrically. If you understand how you can wire stuff up from your 3D model to the PCB, there's something you can add in. This thing is like connected to the terminal block, which is like really dangerous. Like I can feel like it's shocking myself sometimes when I'm shorting it across. In general, you don't want to do this, but I'm using this for another project right now, so it's just a demonstration. Okay. So in this case, if you go ahead and want to CAD something in this divot right here, and you look at it from the right edge, it's going to be hard to do so because you can't really see what you're CADing. So sometimes you like to CAD at an angle, but just understand that you still need to go ahead and understand that it's a flat surface, kind of like tilt it in your mind somehow. So this is 21 millimeters deep, which means 21 millimeters divided by 2 is going to be 10.5. If we make a line in the middle here, again, remember the triangle specifies a midpoint. I can make a line all the way down. And I'm going to make a circle. That's going to be, let's say 5 millimeters, 6 millimeters, 7.5 millimeters. 7.5 sounds nice. Okay. And then all I'm going to do is I'm going to go ahead and extrude this all the way through. Okay. Yeah, like that. All right. At this point, you have to think to yourself, okay, how am I going to print this? Right? If I print this model from the bottom up, then this is going to have a lot of support, right? You kind of want to minimize the amount of support you have while printing. If I print it on the side, that's going to work. If I print it on, let's say this side, let's say this side is touching the bottom, and it prints from the bottom up like this. This is going to work. Oh, hold on. Like this. So if I print it like this side up, it's going to work without any supports. But this bevel is going to be a little bit sketchy. This bevel is going to be a little sketchy to do. So in this case, the correct solution, in which I think is the optimal thing to do, is to print this using belting, using the belt printer. At a 45-degree angle, this is actually going to print perfectly without any supports, right? So the 45-degree printer will just print diagonally. It'll keep printing diagonally like this. And then when it reaches this point, it'll actually connect with the previous junction and allow it to print normally. And it won't need any supports to do so, which is the best part of this. It might need some support here, maybe. Let me think. No, not if I print it backwards. If I print it backwards, like starting from this end, then it'll just follow through and it won't need any supports there. It's kind of hard to explain because a lot of what CADing is mental. But basically, at every point of CAD, if you're going to 3D print this at some point, you have to think to yourself how you're going to 3D print it. And in this case, because I have so many complex shapes, I can't print it using a normal 3D printer. I got to use my 45-degree belt printer to do so. Does that kind of make sense? Okay. So I'm going to put my battery in here and I'm going to wire it through this crescent shape into the PCB on top. Um, and I think the last thing I need to do for this diagram is, or for this model, is to add some sort of battery cover to it. And adding a battery cover is going to be pretty simple in my opinion. I'm going to just create two rectangles from this shape that are going to be, let's say, 5 millimeters deep. And then I'm just going to put a screw hole through it. So I'm going to finish the sketch, and then I'm going to extrude this. Again, remember, it's going to be 2 millimeters deep because that's how much tolerance I gave it. And I'm going to basically just CAD an extra piece that will go on top of this, and it'll screw in perfectly, right? It's kind of like in my Blinky Learner case, in which I had this little divot here, in which I had like a battery cover in order so that you could, just like screw it in like this. But in this case, it would be much wider to compensate for the fact that there's such a large opening for the battery in that case. So I'm going to go ahead and make the holes by creating a sketch on this plane. The plane I'm CADing in is actually this plane right here, which has the 2 millimeter extrusion down into the PCB. So I think I'm going to use a M2.5 by 6 millimeter screw again, but this time these screw holes are going to be only 4 millimeters deep because I already have compensated for that edge. Okay, so in order for me to space these screws out correctly, I'm going to use a divide by 3 method. So I'm going to space this evenly within 3 intervals from the top and the bottom. So what I mean by that is I'm going to measure the top and bottom, which is 26.5, and I'm going to take 26.5 and divide this by 3. This will give me 8.8 millimeters approximately. So to be precise, then I'm going to use a point. And I'm going to draw 2 points on this surface, and I'm going to space them out 8.3 millimeters evenly with each other. 8.8, sorry. 8.8. Okay, so now I'm going to imagine to myself, okay, I see these holes right here. Is this what I want? Is this what I want eventually inside the design? And this spacing looks a bit too close. Structurally, you want these screws to be spaced out so that when you screw it in, it'll be nicely supported by the interior of your design. So in this case, I'm actually going to go ahead and divide by 4 instead. And this gives me 6.625, in which I think 6.625 will be good. 6.625. Okay, so that spacing looks a little bit better. So let me go ahead and finish the sketch, and I'm going to extrude it. I'm going to create holes in these 2 locations with the same settings I used to create the holes on the outer edge. Now these are going to be M2.5 by 6 millimeter screws, so the same settings, but this time they're sideways. Now sideways holes are actually printable by the 3D printer, which is pretty impressive. So these holes will actually print out as long with the upper holes as well. Okay.
Can you mirror those 2 holes to the other side?
Yes, that was my next step. So you got me there. Good forward thinking. So we learned how to mirror sketches. Now we're going to learn how to mirror objects. And I'm going to introduce you to the planes. So in order to CAD anything in 3D modeling, you need to use what's called planes. And there are a lot of planes like the origin planes. The origin planes are the planes in which we started out from, the XY, the YZ, and the ZX, sorry. But there are also object planes. You can make planes based on the object that you are CADing right now. So for example, I want a midplane, right? I'm going to select the midplane, in which the midplane can be created by selecting the 2 edges right here. And it'll make a plane directly in the middle, smack dab in the middle, right? And since these 2 edges are symmetric to each other, all I need to do is I am going to use the mirror, right? But this time I'm going to mirror the features, right? I'm going to mirror the features of these holes. So in that case, I'm going to mirror this. And then my mirror plane is going to be here. Oh, hold on. I need to mirror the right thing. So I'm going to mirror features. Sometimes you have a hard time selecting it, so you gotta. Come on. Oh, there you go. Okay, there you go. So you select the holes, you select the mirror plane, and it mirrors it to the left side. So now you have your threaded holes on both sides of your design, like that. Okay, and then you can just select the mirrored plane and you press V to make it invisible. And there you go. So I've only sketched one side, but now it's on the other side. And this is good because both of them are parameterized. And what it means by that is that if I make a change to this side, it'll also make the change to the other side as well. So if I have to make the hole deeper on one side, it'll make the hole deeper on the other sides. Pretty nice. Okay, so now I noticed a slight problem that I'd like to fix. And the problem is that this crescent-shaped hole is centered when we look at the battery cage. However, it is not centered when we look here. Look at this. It's a little bit deformed. So what I want to do is I want to center on this edge as well, which means it will not be centered on the inner edge, but this allows for us to get a better, just a better outlook, right? Because I care about looks too. So it looks better if it's centered on the outside. So I want to do that. In that case, what I have to do then is I have to go back to the previous sketch, which is going to be over here. This sketch was the one where we went ahead and drew the semicircle. So in order to center it on the outskirts right here as well, I need to go ahead and find out the center between this line and this line, which is 25.40. That divided by 2 is 12.7, which means that the center of this hole right here has to be 12.7 away from an edge. So I can go ahead and dimension this, click the dimension button, click on the center of this circle, click on the edge here, and oh, this will overconstrain the sketch. So I need to delete this line. So in that case, I'm going to go ahead and change this to 12.7. And it moves the entire crescent there. So this is me saying I don't care how it looks on the inside, but then if I look on the outside, now it's centered and it looks nice, right? That's cool. The last part of this is making the cover that will cover this entire area here. So to do that, I'm going to go ahead and make a plane, right? Because I want to start a sketch from somewhere. So I'm going to make a plane on this front surface and I'm going to offset it by like 3 millimeters or 5 millimeters. Now, this is what's called an offset plane. If you want to diagram something, like let's say an extension to one of your 3D models, but you want to do it like from a distance, this is how you do it. So you make an offset plane that's 5 millimeters away. So you look at it from the side, it's not directly touching the surface, right? And I'm going to press OK. And I'm going to go ahead and start the sketch here. Now, I'm immediately going to go ahead and project, right? Project geometry. I'm going to project this outer circle here because I'm going to make a cover for it, right? A cover just so like a small 2 millimeter little rectangle for it. However, I cannot just go ahead and extrude this small little rectangle here because it will not fit. Again, tolerances are really important. So if I just go ahead and extrude this and print everything out, this little area will not fit because the outer part will shrink faster than the smaller parts, and we'll get some tolerance errors. So in order to avoid this tolerance, I'm going to teach you a new command called offset. So in the sketch window, you can go ahead and create a click of the offset and click this rectangle here, and it'll actually automatically create a new sketch for you that is going to be offset from your outside model. So again, I'm going to go ahead and make a 0.5 millimeter offset, or yeah, 0.5 millimeter offset should be good enough for this. So this rectangle is 0.5 millimeters as an offset from the outer diagram. I think actually it's even less, if I remember correctly. So my battery cover is even less from it. Let me see. So having like previous designs really helps you. I think it's 5.08. I think that's 0.25. Let me check. Yeah, so the distance between these two lines here. Oh. It is 0.25 millimeters. 0.254. Okay, 0.254. I'm going to use that instead as an offset instead of 0.5 because this might be too loose. And if you get a dimension wrong, it's okay. You can always just print again, right? It's not the end of the world. Like we are lucky to have enough funding to reprint again and again if we have to. So 2 millimeters, I'm going to create this as a new body. And when I press OK, this sketch will be completed. All right, so we know this divot is 2 millimeters, right? And if we place this inside, it should be flush. It should be flush with the outer surface. And generally, that's true. There is going to be a small little tolerance that will cause it to not be flush, which I think I'll just account for by making this a little bit thinner. I'll make this 1.9 millimeters instead of 2.0. There we go. Okay, so now we need to make the holes. And this was what I was talking about. There are two types of holes in the world. One is a through hole, and the other is the tight hole, right? And the tight hole is just like the threaded screw hole. We're going to make a loose hole here. And the loose hole is really important because it will allow us to screw it in. When we're screwing it in, we won't have to screw the screw through this 2 millimeter thick piece, right? We can just screw it through into this hole right here. Okay. So what we're going to do is I'm going to make a sketch on the surface of this battery cover here, right? And I'm going to go ahead and project the geometry of the back holes. So I'm going to do project geometry. I'm going to project this hole, and I'm going to project this hole as well. Press OK. And I can see I have the center of the holes already on the sketch for me. This is great. So all I need to do is finish sketch, and then I'm going to go ahead and make a hole through here. Now, this hole is going to be a little bit different, and let me tell you why. So in my box of a lot of stuff here, one of them has a lot of screws. So this is a box of a lot of screws, and I have a lot of these storage crates. I bought a bunch of these M2.5 screws that I'll eventually use. I bought these from, it was, what's that company's name? McMaster-Carr. So these bunch of screws have a flat top on it. And the flat top is great because it allows me to screw things in flush with the surface. I have other M2.5 screws, including this one. Oh, this one's kind of the same thing. Yeah, this one's exactly the same thing. I have bigger screws here. These have like a more rounded top. And I have other screws in which we actually have these kind of screws inside of our room here. These are countersunk screws, M2.56 countersunk screws. I don't know if that's clear or not, but the tops have like a horizontal cone-shaped divot that goes into the board itself. So when you're designing, you have to understand what kind of screws you're working with, either countersunk, or counterbore. And in this case, I think I'm going to use counterbore screws to screw this in together. So I have to account for this in my design. I'm going to get a screw just to make sure I have the correct measurements in here. So counterbore screws look like this. They look like the rectangular head shape here. Countersunk screws have the slanted edge, like the rectangular edge. So in this case, I want a counterbore screw. And this screw, I want it to be simple because I don't want it to be threaded, and I want it to be flat. So this is going to be 2 millimeters deep. We already know that. The top of the screw, in which this is the hard part, you got to make sure you have the right tolerances for this as well. So I'm going to go ahead and measure the top of this screw.
So the top of the screw will be sticking out?
We want it to be flush with the surface. So I want the entire screw to fit inside this hole. That's what I'm saying. Like if I match this screw with the diagram here, it should be matching because every screw has the long area and then it has the head, but sometimes the head sticks out, right? And so
wouldn't be using a cone shape, wouldn't that be the flush one? Because this one would be
sometimes, right? The screw shape itself, sometimes it has a cone-shaped head, but this one has a flat rectangular shaped head, right? I can't.
Yeah, I can see it.
Okay, cool. Yeah, so because it has a rectangular shaped head, we want a rectangular shaped hole.
Got it.
Sometimes like I do use the cone shape, like in the Blinky Learner previously, I used a cone shaped screw, a countersunk screw in this, and that's why it looks like a little bit different. But in this case, I think I bought a lot of these screws. I'm going to use it, so I think I'm going to design it like that. And that's just like the general sentiment of hobbyist designers. If you have the stuff, use it, right?
So basically that figure that we see on the screen is basically the hole that the screw is gonna go in, right?
Yep.
Got it.
5.5. So this hole is like 5.5 wide, which is gonna, all right, so now we have a problem because this hole is going to be a little bit too wide, which is fine. I'm going to make it 5 millimeters. Okay, that's not going to work. How thin can I make it with it being still be able to fit in it? 4.80. Yeah, see here is a mistake of not proportioning your holes correctly before you start making them. Okay, that's not gonna fit. We're just gonna say it's 5 millimeters and like yeah, the top of the hole is not gonna fit. Okay, just kidding. Simple hole it is. The width of the hole is going to be approximately 3.3 millimeters. So I'm coming up with 3 millimeters is because I'm giving it a little bit of tolerance, and if I can wiggle the screw around inside this hole, then I know it's good enough. So this is a 3 millimeter diameter hole. Now, the screw isn't going to like screw into this. It's supposed to loosely fit through this hole, right? And this is evident because the hole on the outside is actually bigger than the hole on the inside, right? So we don't want to screw in two pieces of plastic together. We only want to screw into one piece of plastic. The screw just holds this big piece in with the rest of the board. And I know I didn't make a flush hole because it's not going to fit anyways, but it's okay for this example. All right, now let's go. Let's say actually this is okay. Let's say I want to add some like more stuff to it. Let's say I want to put Banshee UAV robotics, right? You can do that by adding text. Now, text actually prints pretty well on PLA for both the Belty and the regular printer. You'll be surprised at how well text prints. And it's really cool because you can personalize whatever you're printing. So let's say I put in, I like to use the font, where is it? The font I'm looking at is this one, the condensed extra. I'm going to put Banshee UAV robotics. And then I'm going to change the height down to like 5 millimeters. I'm going to put it aligned centered like that, right? And then I'm going to press OK. So this is just kind of some personalization things you can do. And then you can go ahead and extrude this. Let's say extruding it -1 millimeters into this surface. And then suddenly you have your very own neat little personalized battery cover that you can screw into this little PCB holder that you've designed as well. Okay. I know the sides look a little bland and I'm tempted to add more things to it, but I'm not going to. Just for the sake of printing this out on a timely manner. I'm really tempted to, because I usually just put stuff on the back as well. If I have more time, and this takes a lot of time, and I'm just going to give you guys an option here. If you can insert a canvas, actually, and let's say I go ahead and insert the Banshee UAV logo. This is upside down. I'm just going to rotate this here. Okay. Now, if anyone is mad lad enough to get me an SVG file of this image here, what you can do is import the SVG file and actually have each of them as divots. Like you can actually CAD this logo straight into the design. And Personally, I would like be tempted to do this, but I don't have the time to. So because you can insert an SVG file and do this automatically, but basically having your logo inside of the actual design, kind of like the Blinky Learner case, where I individually traced every single divot of the CPP image, the CPP Hyperloop image, into the actual design. So if I just get rid of the picture, you can see that this is actually catted in. So it prints really nice, and it's like a really nice memorabilia. So in case you want to actually like make something designer friendly, that's how you do it. But I don't have the time for that. So we are pretty much done with the design. All that's left to do is to make it look nice. Control 4 will get rid of all the lines so you can see what it looks like on the screen. But I'm going to tell you guys one more thing before I send this to the STL file for production. I'm going to go ahead and make sure that all of these are components. So I'm going to teach you guys how to actually join these things together. So in order to actually joint this together so it acts like one body and like not like a separate body itself, I'm going to go ahead and first name my bodies. This is going to be my main body. It's going to be my back cover, so my battery cover. Right. And I'm going to go ahead and right click, and then I'm going to select create components from bodies. So now these are components, and I'm going to go ahead and make sure that this is a rigid group. And what a rigid group is that if I make this into a, if I see how I can move it around, see these little components on here with the terminal blocks and the capacitors and the whatnot. If I didn't have rigid group, this would just like move all over the place. I would only be able to move the PCB and not everything else on top of it. So that's why I have it as a rigid group. Now I'm going to go ahead and use the joint function to go ahead and joint this top PCB piece to the bottom PCB piece here. So if I select this and I go ahead and move this to the top. There we go. Press OK. Then basically what I just did was I constrained these two pieces together, right? So the main body and the PCB are now one piece together. Will the cover be printed horizontally flat separated from the main body? Correct. I will be able to print this little piece separate. So I'm going to joint the front piece now, so this front piece here, into the hole on the front. And I can just adjust it if necessary. And theoretically, I do want this to be flush. Okay. All right. So now, this is pretty much it. So we have created a PCB mount for our voltage regulator with a battery compartment on the inside and personalized text via the Banshee UA Robotics symbol in front of the battery cover. The final step is to turn this into an STL and actually print it on some 3D printers. So in this case, I'm going to go ahead and click on the body. I'm going to right click it. I'm going to click export. And then I'm going to go ahead and export this as a STL file. Actually, I'm going to go ahead and save as mesh first, because that's how you save it as an STL file. So under mesh, you have the ability to send to a 3D printer file, like a 3D print utility. Unfortunately, the Belty 3D print utility is on my other computer. So if I want to start this print on Belty, I'm going to have to slice it on my other computer. Slicing is the action of turning the mesh into something the printer can actually recognize, a G-code file. So the printer will take these G-code instructions and move the stepper motors to actually print the diagram you want. So in this case, I'm going to go ahead and just save this as a STL file. I want to make sure I have the unit type as millimeter, and I'm going to click OK. And then here I'm going to go ahead and go into my Robotics file, and I'm going to save this as a main body. It's going to be vreg. Okay. Now I'm going to show you what it's actually like to slice it. I'm going to slice the battery cover for you so you guys can see how the printer will interpret this diagram as actual instructions to start printing it out. So I'm going to save as mesh, but this time I'm going to save it as send to its 3D print utility, and my 3D print utility is going to be Cura. So I'm going to press OK. Okay. Come on, Cura, open up. I did send to Cura, right? Oh, Cura just opened up. All right. So this is what I see when I slice the diagram, right? Cura is kind of like the gateway between your STL file and the 3D printer's G-code files. So in this case, I have my little image over here. I don't know why there's like a little bit of a shadow there. I'm going to go ahead and right click this and click Arrange All Models and bring this up into view. Okay. Then I'm going to rotate this so that it's flat on its surface. Like this. All right. So in my mind, I'm thinking, okay, this battery cover is going to print from the bottom up. And so if I go ahead and press the, I'm going to use my S1 PLA to print this. And each 3D printer has different settings. I'm just using, I have like a lot of different settings for printers I have here. If I go ahead and preview this, you can actually see how the printer is going to print this piece out, right? You have layers on the right. So if you scroll down the layers, you can see the printer initially prints the first layer, and then the second layer, and then the third layer, fourth layer, fifth layer. And on the fifth layer, you can see it actually starts to print some of the support structure in orange and the actual text, the Banshee UAV Robotics. And then it keeps going, right? So all I need to do now is I'm going to go ahead and rename this to UAV, and I'm going to say VREG back cover. And then I'm going to take my SD card from my printer, shove it into my computer. And this whole stuff comes up because I have a lot of files. I'm going to save this, eject, and then I'm going to print it in my 3D printer. Okay, I haven't used my 3D printer in a long time, so I actually have to do some maintenance to clean up all the dust and stuff. I'm thinking of actually getting some printer covers to prevent dust from happening because I'm a very dusty person. But I will be posting pictures and videos of the items printing, both the battery cover and the voltage regulator, after this meeting concludes in the robotics server, just so you can keep up to date as to how this is going. I'm not going to show the entire printing process. But as of right now, are there any questions as to CADing and how this is made and how you should 3D model things? All right, if not, that is going to be it for this workshop, this CAD workshop, the final workshop I'm doing for the summer internship. Thank you all so much for coming and watching. And I hope you can take these skills and complete some of the required tasks on the Gantt chart yourself. And as always, if you have any questions for those of you who are watching this that are not in the Zoom meeting and watching this later, you can always feel free to ask me through Discord or text me in the Discord channel. All right. So if that's all, then I hope you guys have a great rest of your day, and I hope to see you sometime later. Thank you guys. Bye-bye.